The world, as we know it, is decarbonizing. To avoid the threats of climate change, we are shifting away from fossil fuels towards clean, renewable energy. However, the crux of renewables has been their intermittency. For example, solar produces the most energy in the daytime where demand is the lowest, and produces the least amount of energy in the evening where demand is the highest. This has led to energy storage becoming the most critical factor for clean energy systems. This can take many forms, but one of the most promising is batteries. A highlight example is Tesla's battery storage facility in Hornsdale, Australia, which provides 1 gigawatt hour of storage equivalent to 10,000 Tesla Model S electric vehicles. Batteries are important in many other aspects, such as consumer electronics, as well as clean electrified transport. However, some argue that batteries for clean energy is a hypocrisy. They have been flagged for their high carbon footprint, depletion of scarce resources, and unsafe disposal of toxic materials. How true and threatening are these claims? Will a solution to a global problem create a disaster elsewhere? Will batteries destroy or save the planet? Batteries blew up in the 20th century, with lead and nickel batteries fueling the age of consumer electronics. Nickel batteries even made it into the first commercial electrified vehicles, most notably Toyota's hybrid, the Prius. However, a new battery chemistry was on the horizon. In the 1970s, Professor John Goodenough and his research team developed a new battery chemistry, the lithium ion. Sony went on to commercialize the battery in 1991, and the rest was history. So, what was the hype about these batteries? Well, compared to other batteries, the lithium ion had major advantages. For example, it had a much higher specific energy, which is the amount of energy the battery can store per unit of mass. It had a higher specific power, which is the amount of power the battery can put out in one go. And also, it had a much longer lifespan over other batteries. But despite this, compared to its nickel counterpart, the lithium-ion battery was very costly. However, 2015 marked the year where the lithium-ion battery broke even with nickel batteries, dropping to prices below $300 per kilowatt hour. Today, this price is at $150 per kilowatt hour, fast approaching to break $100 per kilowatt hour. The superiority and rapid cost reductions of lithium-ion batteries unlock their scalability in energy storage. But what does a lithium-ion battery actually look like, and how does it work? In simple terms, a rechargeable battery is a device that can store and release energy by converting between electrical and chemical energy. One of the most common lithium-ion chemistries is NMC, standing for nickel, manganese, and cobalt. At one end of the battery, there is a positive aluminium cathode coated in the active NMC material. At the other is a negative copper anode coated in graphite. These are separated and filled with a lithium salt liquid electrolyte. When the battery is charging or discharging, the lithium ions move between the electrodes, storing or releasing energy. For more battery science, check out Zeroff's video on Tesla's million-mile battery. So with so much hype on lithium-ion batteries, why has there been so much concern? Let's begin with the supply chain using electric vehicles as an example. Raw materials from mining would supply a battery manufacturer such as LG Chem in addition to other pre-manufactured materials. LG Chem would process these materials into battery cells before shipping them to an EV manufacturer such as Tesla, who would incorporate the cells into an EV battery pack. Once sold, the EV batteries would be used for around 8 or more years, after which Tesla would collect the batteries and treat their end of life responsibly and safely. So, where and what are the problems? Let's look at the carbon footprint of manufacturing. For every 1 kilowatt hour of battery produced, or around 3 kilograms of battery, 100 kilograms of CO2 equivalents are released across its life cycle. For a daily comparison, 3 kilograms of beer would only release 3 kilograms of CO2 equivalents. The reason for the carbon intensiveness of batteries is simple. 65% of these emissions arise from the high energy consumption for the machinery and drying processes used. The rest of the emissions are from packaging and other components and the NMC cathode materials. But why are these energy emissions so high when the world is decarbonizing? Well, the answer is China. Globally, 63% of all batteries are manufactured in China, where the electricity is carbon intensive, with coal making up 62% of the mix, whereas in Europe, coal makes up only 12% of the mix. So yes, it seems that the claims about the high carbon footprint of batteries rings true. But what about the use of scarce resources? Scarcity concerns center around two elements, lithium and cobalt. Globally, the battery industry is a major consumer of both elements, accounting for 50 and 40% of all lithium and cobalt flows, respectively. For lithium, estimates show there are 80 million tons of lithium reserves. In 2020, around 82,000 tons of lithium were mined, which means at current extraction rates, there would be nearly 1,000 years of lithium stores left. Even with increasing demands, I don't see lithium being a problem. With cobalt, however, the story is different. Estimates show we have around 7.1 million tons of cobalt reserves, although we're not sure about the undiscovered amounts. Nonetheless, in 2020, around 110,000 tons were mined, meaning with current extraction rates, we have around 65 years of cobalt left. With rising demands, this is a lot more worrying to me, but not for the reason of running out of cobalt, but to the lengths that the industry will go to finding more, especially in the emergence of deep-sea mining. With our current global record of spilling 70 million barrels of oil over nearly 300 cases, I am not confident about deep-sea mining of toxic metals. Indeed, cobalt is a scarcity issue, but this is not the full story. Cobalt has a dark truth. 59% of global cobalt production comes from the Democratic Republic of Congo. 30% of mining conducted is through artisanal methods, which are unofficial small-scale operations using raw methods. The miners are some of the world's most poor, involving 12-hour back-breaking shifts using hand tools without protective equipment, while earning as little as $2 a day. To more alarm, it is estimated that nearly 40,000 children are among the workers. This has begun to be seen in the light of media, with families bringing lawsuits to big companies such as Apple, Google, and Tesla over multiple deaths in cobalt mining. For how much control big companies have over their cobalt supply chains does remain a mystery. We can see that there is more than meets the eye with the upstream impacts of batteries, but what about the downstream impacts? In the automotive industry, manufacturers are required by law to take back their batteries for safe and responsible end-of-life processing. At least that is the case for Europe. Due to the recency of lithium-ion batteries in EVs, most are still in use, meaning there is limited data on the end of life of these batteries. Though, concerns of battery collection are rising. For example, Tesla was recently fined in Europe for failing to take back their batteries. Moreover, when we look at the recycling rates of portable batteries, in 2018, Europe's recycling rates were only 48%, with the rest most likely ending up in landfill. This is highly problematic given upon corrosion, battery chemicals and metals leak, contaminating land and water. But for the batteries that are recycled, how effective is recycling? There are three methods to recycling batteries. The first is pyrometallurgical, or pyro for short. This involves crushing and smelting batteries to create a mixed alloy which can be separated further. The second is hydrometallurgical, hydro for short, which also involves the crushing, but then leaches the batteries to separate the independent elements. The third is direct recycling. This is physically recovering the original components without energy or chemical intensive methods. For simplicity, pyro is the less accurate, brute force method that recovers less. Hydro is a less intensive, more accurate method, but it's challenging to tailor a single process to multiple battery chemistries. Direct recycling is the simplest and most regenerative practice, but it requires rigorous sorting and relies on the battery actually being designed for easy dismantling. The combination of these methods can achieve a high recovery of battery materials, avoiding the need for their primary demand, therefore having great environmental savings. However, the challenge lies in the economics. More expensive batteries have a greater incentive for recycling because this has a greater cost saving compared to the cost incurred for the recycling. But when we take the less expensive batteries the industry is moving towards, these do not have a good recycling incentive because they offer lower cost savings compared to the cost for the recycling process. For example, a NMC 111 battery will have recycling cost savings of 6% by pyro, 13% by hydro, and 27% by direct recycling. But the NMC 811 battery, which significantly reduces the amount of expensive cobalt used, when recycled will incur costs by 6% using pyro, only save 1% by hydro, and save a respectable 16% by direct recycling. The economics of battery recycling is a conundrum, but what is currently being done? In Europe, there are currently 11 major lithium-ion battery recycling centers, most of which use pyro and hydro methods. Simply due to the variety and lack of standardization of batteries, direct recycling is very difficult to scale. Combined, these centers can recycle around 50 kilotons of batteries annually. Currently, there are around 1.75 million EVs in Europe, with a total battery stock of 375 kilotons. Now, while those numbers don't match, given that the income of the waste would be stagnated, I am confident we have the recycling capacity. However, under current EU policy measures, if achieved, 2030 could see 35 million EVs on the road, amounting to 7,500 kilotons or more of battery stock. So, recycling capacity will need to ramp up. Nevertheless, the challenge remains in the collection of batteries, recycling economics, and standardization of battery design. There are more sustainability issues with batteries that I could discuss, but in my opinion and estimations, I believe that the carbon footprint, cobalt supply chain, and recycling economics are the greatest threats to sustainability, and it's time to do something about it. Let's come back to the carbon footprint. In theory, decarbonizing battery manufacturing is straightforward. First, we need to replace coal with natural gas, which lowers the life cycle CO2 emissions by 40%. In parallel, ultra-low emission renewables such as solar and wind need to be rapidly deployed. By 2030, China plans to increase its share of renewables up to 24%, and for them to dominate from 2040 onwards. Therefore, long-term decarbonization of batteries is inevitable, but what can we do in the short term? Well, as mentioned, 63% of batteries come from China, so another solution is to distribute the manufacturing to locations with cleaner electricity. For example, by 2030, Europe plans to generate 54% of their electricity from renewables and nuclear. Based on the current carbon footprint of batteries, moving manufacture to Europe can mitigate 85% of these emissions. In fact, Europe is already looking to expand its battery manufacturing capacity from 30 GWh to over 300 GWh by 2030, with some estimating Europe to have 25% of the global battery manufacturing. This is a step in the right direction. Furthermore, Europe will enforce the declaration and regulation of battery carbon footprints from 2024, which will further motivate manufacturers to decarbonize their batteries. But what can we do about the cobalt? The priority is to eliminate cobalt out of batteries, but this is difficult given cobalt is key in the chemistry in providing high specific energy and battery life. The industry does recognize the cobalt problem and is already shifting to NMC 811 formulations, which reduce the amount of cobalt used by 70% compared to other NMC formulations. But in my opinion, there is an even better choice. It is the lithium iron phosphate battery, LFP for short. This battery not only eliminates cobalt, but uses iron and phosphate materials, which are cheap and abundant. For sustainability, this is an ideal battery, and has already been popular in China's electrified fleets, and Tesla is already incorporating these batteries into their Model 3s. However, these batteries still only account for 20% of the market share. So, if this battery is so sustainable, why isn't this number greater? It is the battery's practicality. The battery is not commercially attractive, given it has a lower specific energy leading to either a shorter range or a heavier vehicle. Moreover, the battery experiences charging problems during cold weather. But promising solutions are emerging. For example, researchers from the Pennsylvania State University have demonstrated to eliminate the charging issues and boost the battery properties by thermal modulation methods ready for mass market of LFP batteries. There are also new emerging battery chemistries that eliminate cobalt, such as lithium sulfur and sodium ion, but these still have a long way to go. For now, rapid reduction of cobalt in NMC batteries and rapid scaling of LFP batteries are the practical strategies for the industry to mitigate resource scarcity and the human rights problems in Congo. Now, let us confront the end-of-life and recycling economics of batteries. We need to phase out intensive pyro methods towards more economically and environmentally favorable hydro and direct recycling practices. Now, while I can discuss innovations in recycling technology with companies such as LI Cycle and Umicore that are improving recovery rates and cost savings, I believe the best solution for end-of-life is actually elsewhere. The challenges stem back to the design of batteries. Currently, most batteries are designed rigidly sealed and are not standardized, giving companies, of course, want to protect their secrets. But this is the fundamental reason why recycling is locked into intensive methods and has such difficulty. What if we design batteries with a new philosophy, one with the intention of multiple lifespans, those that disassemble with ease and can easily separate components for superior tailored recycling, or better, separate components which can be easily reused or remanufactured for a new battery. This strategy is part of the circular economy, which will not only mitigate the end-of-life challenges, but relieve challenges in resources and offset the carbon footprint. For example, one startup, Acceleron, is replacing traditional welding and gluing of batteries with compression methods that enable easy disassembly and separation of battery packs in the end of life. Now, when EV batteries are spent, they still have up to 80% of their capacity remaining, which can last another 10 years in lower power applications such as energy storage. For example, Renault partners with PowerVault to repurpose used EV batteries in home storage, with these repurposed batteries reducing the cost of home storage by 30% for consumers. Moreover, there would be a market for repurposed EV batteries for the ever-increasing grid energy storage, as well as off-grid energy access in developing countries which could massively benefit from the reduced costs of these batteries. However, to repurpose these batteries, they may need to be remanufactured for the new application. But the researchers at the University of Warwick have already designed a low-cost remanufacturing method of a battery management system to repurpose EV batteries from the Nissan Leaf towards home storage. Combined, I believe these circular economy strategies are the best but often overlooked approaches to mitigating not only end-of-life problems of batteries, but those across the whole supply chain. However, as exciting and as practical as these strategies seem, these are still niche examples without much intention for mass scaling. Therefore, policy is critical. For example, Europe is looking to aggressively increase battery collection rates, and with the enforcement of the carbon footprint of batteries, to also enforce the amount of recycled content that each battery would need to have, as well as declare the sustainable sourcing. This will be key to incentivizing battery manufacturers to scale circular economy strategies. So with the strategies of decarbonizing manufacturing, eliminating critical materials, and deploying the circular economy, can batteries truly achieve sustainability, or will they be another downfall? The sustainability of batteries, as with many other things, is a complex discussion. I believe by 2030 we will have moved to more sustainable practices, and by 2050 I am confident many of the issues will have been dealt with. But I am also confident that there are many undiscovered unknowns, ones which will present new challenges in sustainability, ones that after fossil fuels will inevitably crown batteries as the new antagonist. But in the present moment, I believe batteries are the best option for energy storage of renewables, and in my opinion, a much better scenario over the alternative. But this is no excuse to deploy problematic batteries. and I hope to have shown you in this video that we do have options for batteries to be made more sustainable. Without the will to act, batteries will simply be a transfer of problems from one place to another. But with the will to act, batteries may just be a key part in not only avoiding Earth's climate disaster, but to achieving global sustainability. If you have made it this far, thank you for watching this video. I hope to have earned your like and subscription. So Atlas is a YouTube channel that will discuss global sustainability transparently and analytically, seeking to engage you in research and critical thinking through narratives. This is quite a big video that I hope has given you a strong flavour of what to expect, although I expect for future videos to be shorter and a bit more focused. If there is a specific sustainability topic you want me to discuss next, comment below and let me know.